of chemistry. Yay! Right? So let's talk about hydrogen bonds. So hydrogen bonds are just basically looking at interactions between a hydrogen that is in a polar bond with something else and say an electronegative atom like nitrogen or oxygen, right? And so it's this kind of slightly positive charge from a hydrogen to slightly negative charge of something else. It's not a true bond, it's more like an interaction, and you see it a lot in water. So if you've ever washed like a cookie sheet and had water on it or something and put it on the countertop and then you couldn't pick it up, that interaction, that is a bunch of hydrogen bonds. It also acts as an intramolecular bond holding some large molecules in three-dimensional shapes together. So let's look at what I mean. So these are individual water molecules, and as you can see, this is the basically slightly dipole or electronegative action, right? You have slightly positive at this end, slightly negative here. And you can see the same things happening here, right? That you have the slightly negative coming down here and the positive here. This is the hydrogen bond. This guy is slightly negative because of that polar bond that it's forming with hydrogen. This is the slightly positive, the hydrogen, due to the polar bond it's forming with oxygen. So that slight negative with a slight positive here, that interaction, is what is considered a hydrogen bond. Now, they're very weak unless there's lots of them. And in hydrogen or water, there's lots of them, but it depends on the temperature, right? And so water is this really, really cool thing. And hydrogen bonding is going to affect a lot of different properties of water. For instance, water has a higher boiling point than it would be deduced through normal chemical means this way if it was anything else. And it's because it has a higher boiling point because it has to break this hydrogen bond first before it can like evaporate, or the point of evaporation. So that's why when you sweat, water is such a good way to get rid of that extra heat, because it has to break that bond and then it evaporates. It's called the heat evaporation. So where it evaporates, or the boiling point as well, is higher because of hydrogen bonding. You know that water, the solid form, actually floats versus the liquid form. Think of ice. That's weird. Is there anything else where the solid really floats, right? And it's this idea that normally solids are heavier than liquid or gas forms and they sink. But in the case of water, because they make this beautiful, nice crystal arrangement here that puts each water molecule a perfect distance away, because the molecules are moving slower, you're able to get this one, this one, this one, and this one. So they push them farther away, which means there's less molecules in an area, so it becomes more or less dense and it floats. Where if it's liquid, they're moving around and it's only about 3.2 of these that get made versus 4. So liquid water is denser than this. Now another cool aspect of water is this little guy. You have these little bugs that can walk across water, and that's because surface tension is a result of these hydrogen bonds forming even stronger at the surface. Because if you look at this, right, in here, if this was above, right, the water, well, now you can't do this because it's air. So this will rearrange and make these bonds, and even here, stronger on the surface because it can't form hydrogen bonds above it. So these bugs and different insects can use that to their advantage to be able to not fall through the top surface. Water is also an amazing solvent. It has a capacity of hydrogen bonding, and its polarity makes it a great solvent, so it can move around. So you can see here, sodium chloride, without the presence of water, it's strong. Sorry, guys. And you can see they're there. But once water comes in, it's able to make this solvation sphere around it, and it can interact really well with these different ions, and allows it to be an amazing solvent to a lot of molecules. So in a biological system, which one of these is the strongest? Covalent, and then ionic, then hydrogen, right? In the biological system, because of what? Because there's water present, right? In regular chemistry, just to let you know, ionic bond is the strongest. Now, when we're talking about how chemical reactions happen, they're written like this. Chemical reactions are written where you have on one side, you're going to have what are known as reactants, and then this means becomes, and on the other side are products. The number of atoms always remain the same, but they can appear in different combinations. Now, there are four major types of chemical reactions we talk about. There's synthesis reactions, and that's where basically you have two reactants will become one product. You have decomposition, which means you have one reactant and it basically breaks into two products. You have exchange. If you see A, B come in, and C, D, and this is almost like they swap partners, right? Now all of a sudden you have these two together and these two together. So that's exchange. And reverse just means they can go back and forth. This happens basically in water all the time. So these are the main types of chemical reactions you can see when we are looking at them in the lab. Now, these are showing some chemical reactions that can happen, and within our body, there's going to be all types of things that are happening. And we, no matter what waste products are produced, no matter what's there, we have to try to balance those things. And so we have a lot of byproducts being produced that can make our blood more acidic or more basic. And so acids and bases are these things that are molecules that when they dissociate, they release different things. Acids, this is a perfect example here. We're going to talk about these in the lab. Hydrochloric acid. When it is in water, it dissociates, and dissociate means to break. It breaks into two pieces, a hydrogen and a chloride. Ions are those molecules that when they dissociate or break up in water, they release hydrogen ions. Bases are electrolytes. Electrolytes are these things that help to conduct electricity, and they are composed of these two components. And when bases dissociate in water, they release what are known as hydroxides. And hydroxides are important because when they combine with a hydrogen, they make water. So these guys basically pull hydrogens out of the solution and neutralize them, basically. Now, acids and bases can react, and when they do that, they form water and salts here. And that's how you can neutralize the two. Now, when you're talking about acids and bases, we can measure them on a pH scale. And they have inverse relationships. So the lower the number is on the pH scale, the more hydrogens are present. The higher it is on the pH scale, the more hydroxyls are, so the less hydrogens are present. And you can see blood is around 7.4, so it is actually slightly basic. The only thing that is neutral is 7.0. Anything above or below that is going to be slightly basic or slightly acidic. So which one has more hydrogen ions, acid or base? Hopefully you said acid. So when we talk about which one's worse, let's watch this quick video so you can figure it out.
What's being generated over there in the acid can, oh my word. We're going to show you something about aluminium today. And the thing is, we've got here Coke cans and Pepsi cans as well, so that it's fair. But when Neil gave them to me, I had a look inside, and you can see there, this one has quite clearly rusted. So these Coke cans are made of aluminium, whereas the Pepsi ones are steel. That's why we can only use the Coke cans to do this next experiment. So what we're going to do with these is to show a property of aluminium and how it reacts with both acid and with base. And that means it's a substance that's amphoteric. What we're going to do is we've got a solution of sodium hydroxide, that's our base, and we've got also hydrochloric acid, and then Neil's going to put the acid in and I'll put the base in at the same time, and we're going to see what happens to the aluminium cans. Here we go. Oh yeah, straight away you can see the bubbling there with the base. Clearly you've got a very vigorous reaction in both cases. So what's being generated here is sodium aluminate. What's being generated over there in the acid can, oh my word, is aluminium chloride and water. We expected reaction with both, yeah, I hadn't anticipated to be quite so vigorous. I hadn't expected it to be quite so, wow! That is brilliant. So this is obviously a very vigorous, hot reaction. You've got a lot of fumes being given off, which is a good job why we did it in the fume cupboard. You can see all that smoke being drawn up into the extraction fan. I honestly thought the acid would have done more damage. Because when you think of acids, you always associate acids as being the evil guy of the chemical world. I think those Pepsi cans have gotten off very lightly. They may have had their tops cut off, but they've met a fate far better than the Coke cans here. Good old Pepsi for making them steel. Neil, can you clean that up for us?
So hopefully you figured out here that they're equally bad. I mean, in your body, you don't want your blood to be any more acidic or any more basic than homeostasis wants it to be, or that your body needs it to be. And it's important, the pH is so important because you have important proteins in your body functioning, and they only function at the right pH. And outside of that, either way is detrimental to their function, and they'll fall apart and then they won't work anymore. So everybody always thinks that acid is so bad when in actuality they both can be equally bad. So hopefully you've started your Mastering A&P homework and things are going well for you, and we will be in lab here talking about these things, and if you have any questions, please let me know. Other than that, I will see you guys soon.